Hello everyone, in this video I'm gonna briefly talk about what I did in this quarter. So basically what I did is that I used TensorFlow in Python to develop a face mask classifier. I believe that with the outbreak of COVID-19, it is important for us to learn how the computer recognizes our faces. I'm also gonna go over some of the brief applications of it, but I will not come to it until relatively later. In this project in particular, I'm going to use approximately 1600 images of people wearing a mask and approximately 900 images of people without wearing a mask. When reading this data, I'm also going to give them sort of a label that tells us whether they're wearing a mask or not, so that we can use it for later training purposes. As we can see over here, these are some of the sample images of people without wearing a mask, and these are people wearing a mask. When reading in an image, the computer transforms it to a matrix type. So for this part, I'm going to define a pre-processing function that I can apply to all images once and load all of them simultaneously. The first part of this function is establishing a connection to the repository where our images are located. And then we're gonna delete some of the unnecessary data types like ds-size store in case it confuses our training process. And finally, we're gonna resize this to an array for better interpretability. As we can see, when we apply our function to our dataset, we get two labels, with 0 corresponding to the one without mask and 1 corresponding to those with wearing a mask. When we analyze the baseline performance of our dataset, we see that approximately 63% of our images are those people wearing a mask. After the pre-processing process, I'm going to perform the training test split on our dataset and split it into the training set and test set with a ratio of 9:1. The next part of this project deals with data augmentation. I believe that in order to make our model more comprehensive, we have to take into account instances where images are randomly flipped or randomly rotated. As a result, we also have to incorporate these two layers in the Cura set, namely random flip and random rotate. As we can see over here, these are the results we get after we apply the random flip layer, and these are the results we get after we apply the random rotate layer. So the next part of this project is building the machine learning model itself. And for this project in particular, I'm going to adopt a sequential machine learning model. As the name might suggest, this model processes the data using all of these layers in sequential order. We have over here the random flip and random rotation model, which we discussed in our previous data augmentation part. And besides that, we also have a few convolutional 2D layers, max pooling layers, and finally we have the flattening layers to stack the outputs, and the dropout layers to avoid overfitting, and finally the dense layer with a parameter of 2 that corresponds to the number of dimensions, which is namely with or without having a mask. As we can see in our model summary, we have approximately 34 million attributes, and after we compile our model using the selected optimizer, loss function, and metrics, we're going to apply it to our training set. After around 20 training epochs, we see that our validation accuracy stabilizes to well over 90%, which is pretty decent. And after we plot our training process, we also see that there's also no apparent sign of overfitting. And finally comes to the part when we evaluate our model on a test set, and it also achieves a very satisfying 94.5%. Besides evaluating my model in a holistic approach, I would also like to see how it performs on specific groups of my dataset, namely Black people, white people, and Americans. As always, I define a function over here to make my life easier. And we can see that it achieves at around 85% for Black people, 85% for Asians, and around 95% for whites and Americans. This might sound a little counterintuitive because Asians make up the majority of my test dataset. I presume the reason behind this is that Asians itself is a very heterogeneous group, and the program might have a little difficult time analyzing the difference and learning about it. To address this racial bias, I decided to use another well-established model called MobileNet v2. After reading in this model and adding it as another layer to our pre-existing sequential model and fitting it on our training dataset, we can see that it boosts our validation accuracy by a huge margin. With our previous model achieving at around 91 to 92%, this one manages to stabilize at well above 95%, achieving a final accuracy at around 97 or 98. Besides the fact that it didn't show any apparent signs of overfitting throughout the 20 training epochs, eventually a 96% validation accuracy among Black people, 95% for Asians, and also 96% for white Americans shows that the new model manages to decrease the racial bias by a significant margin. Finally, by taking a look at my project with a more holistic point of view, I managed to construct a very effective static image classifier. However, the implication of static image classification in real life is limited. For instance, it is obviously impossible to use such techniques in big transportation hubs. Besides, my model performs classification instead of recognition. I believe that with better hardware and software at my disposal and a more comprehensive dataset, a real-time individual-based face mask identifier could greatly reinforce the security precautions in densely populated areas, and in turn, reduce the risks of spreading infectious diseases in large pandemics. With all that being said, that will be it for my project, and thank you for listening.